All right. Stuff I wanted to talk about today. Two things basically. They're related a little bit. But I want to talk about amplifier classes, and that part will be slides. And then I'm going to talk about how we can convert an analog signal to a digital signal, and how to do the reverse of that, the digital signal, and convert it back to analog. And there's a lot of different ways you can do both of these processes. I'm going to talk about kind of two specific ways. We might talk a little bit more about this on Friday. There's another method of going from digital to analog that I do want to talk about, and we still have time. Probably won't have time. All right, so there's a lot of different ways that we could classify amplifiers. We could do it like power amplifiers, where you just need a whole lot of power being amplified, lots of current, lots of voltage. You could have audio amplifiers that are specifically designed for audio signals. We could have another way of classifying those is effectively how they work. So in that classification scheme, we kind of have two different types of amplifiers. The first is a conduction angle amplifier. These are the amplifiers that we've already talked about. Conduction angle is kind of a weird term. It's just talking about how long the amplifier is on during one cycle. And what I mean by one cycle is I have a sinusoidal wave. So I've tried to isolate one single period here on the left. So that's my input signal. The conduction angle amplifier is referring to how long it's actually amplifying relative to one period of the input signal. Right? The reason it's called conduction angle is because one period is 360 degrees. That's the conduction angle, is how much of that period the amplifier is turned on for. And these are going to come in 4 different classes: A, B, AB, and then class C. The other type of amplifier that's really common now is a switching amplifier. And the way that this works is it's a digital amplifier. So the very first thing it does is it digitizes the signal that's coming into it. That's what this pulse width modulation is. I'll talk more about that when we get to these, but it's basically converting your input signal that you want to amplify to a digital signal. When you amplify the digital signal, then you convert it back to analog. Big difference between the switching amplifier and the conduction angle amplifier is that switching amplifiers, the transistors are either fully on or fully off. They're either in saturation mode or cutoff mode. Conduction angle amplifiers, the transistors are in the linear mode the entire time. So this picture shows a whole lot of stuff going on. Some of the basic amplifier classes. The conduction angle amplifiers increase in efficiency from A up to C. So you can see, hopefully from this picture, the class A amplifier is on for the full period. Right, it's on full time that you're getting input signal. That has benefits and drawbacks. As we increase the efficiency, we are lowering how often, how much, or how long our transistors or our amplifier is on. That's one of the reasons that these classes B and C are more efficient. They're not on as long, so they're dissipating less heat. Then up in the right corner are all of the switching amplifiers. Those can get really high efficiencies if you're willing to deal with essentially a digitized signal. So I just want to go through the 4 different conduction angle amplifiers individually, and then we'll talk about the switching amplifiers. Class A amplifiers are they're the lowest efficient amplifier, lowest efficiency amplifier. They are also the lowest distortion and highest linearity amplifiers. So even though they're not as efficient, they have their place because of their high gain, high linearity, and low distortion. What I mean by high linearity is that if that's my input signal, it's a sine wave for simplicity. A linear amplifier, so this waveform is fed into the amplifier. Every point on the wave get amplified the same amount. That's a linear amplifier. That's usually what you want, is a linear amplifier. You want a faithful reproduction of your frequency. Nonlinear amplifier is just what it sounds like. You would have some component that would be proportional to maybe the square of the signal. So if you got to higher signals, higher amplitudes, maybe you got more gain. Or maybe it's nonlinear in the opposite way, where as you go to higher amplitudes, the gain's not as good. that would give you a distorted output. So, benefit to class A is they're very linear. That's what makes them really good for audio amplifiers. Linear, they don't have a lot of distortion. What they're not good for is something like a power amplifier, where you're just wanting to amplify not just like a voltage signal, but like a voltage and current. These are not as good for power amplifiers because they are on the whole time. What do I mean by it's on the entire time? If you look here at what's hooked up to the base, it's the regular voltage divider base biasing that we've done for like all these transistor amplifiers. The benefit to that is that you can lift up the whole signal so that the entire signal is being amplified. Remember, if a transistor gets a negative signal applied to the base, that's where it's completely cut off and it doesn't do anything. If my signal is both positive and negative, and I want to get that entire signal replicated, I have to have that whole signal be positive. So vary, just my bottom, my lowest voltage level has to still be enough to turn the transistor on. That's what this biasing network is doing. Drawback is that the transistor is on 100% of the time. It's always having current flow through it. That makes it thermally less efficient. All right, class B is a huge improvement on the class A amplifier as far as the heating goes. So basically the idea is instead of making one transistor do all the work, have it be on all the time, you split up the signal essentially between two different transistors. One of them is a regular NPN transistor, that's the top one. The bottom one is the reverse type PNP transistor. It's there to handle the negative signal. So, why is this more efficient? There's no base biasing. I don't need any extra voltage or current to lift up the base so everything's positive. I just let the input signal do that. So the not having to do the base biasing is the secret to this increase in efficiency. The double transistor is also why this is called a push-pull amplifier. When one of them's not working, the other is. Like clip-on toe clips for bike, clipped into your pedals. When one foot is pushing down, the other can actually be lifting up. Push-pull. That's kind of what's going on here. So what's the drawback? Drawback is what happens at zero cost. And that's where we get some distortion. So pretend that's a uniform length period of sinusoidal wave centered about 0. So it's positive the same amount of time as thing. So in this case, the top part of that would be dealt with by top transistor. When it goes negative, that's handled by bottom transistor. It all looks fine. But what we haven't thought about is that it actually takes about 0.7 volts to get the base emitter junction to turn on and start working. Oh, and what that means is that you have a range that range is plus minus 0.7 volts, where the transistors aren't really able to fully turn on or off. That's this distortion at 0 cost. You have the transistors effectively not amplifying effectively this region. So more efficient, the price you pay for that efficiency is this distortion at the 0 cost. So how do we fix that? That's the class AB amplifier. The class AB is really, really cool. It takes some of both of these, A and B, the best of each, and puts them together. So what's different here is now there's a little bit of a biasing network. And I'm putting in these extra diodes here. Kind of boost me up. Just that little bit of this, so this range here where I've got that distortion. That's if I could lift up this whole waveform by just 0.7 volts, I could get this entire peak here where the transistor is turned on. Then I have a little bit here, this part I circled. That's now the part that would be getting the 0 crossing distortion. But that's okay to have that little bit of zero crossing distortion here, because when I switch to the bottom transistor, it's going to have the exact same thing, but its distortion will be where I'm already able to fully amplify. So it's like just, it's giving a little bit of extra positive voltage for this top part, and a little bit of extra negative voltage for the bottom part. That's why there are these two diodes, D1 and D2. They're pushing up and down that voltage level by plus minus 0.7 volts. Class AB amplifiers are really good. They are low distortion, but linear. They're more efficient than a Class A amplifier, a little bit less than a Class B. So A, B, and AB are the most common types of conduction angle amplifiers that you're going to run into. The Class C is a little bit strange. It's the most efficient one. It's most efficient because it's not on for very long. Basically, this ends up being fairly heavily biased. So you kind of think of this as really capturing like the top part of that, like it's pushing that where we only biasing so much, we're really only seeing this top part. And this one that I'm showing you the picture of here. So this is a common use for Class C amplifier is for high frequency use. And what they put in that is a little LC tape circuit to help to signs resonate at whatever frequency you want to amplify. That way it kind of gives it another boost of it. Drawback to the Class C is that they're very non-linear. So they suffer from they can suffer from a lot of distortion. So you would use this for a high frequency amplifier, not for an audio. Okay, any questions about the conduction angle amplifiers? If you were to build a conduction angle amplifier out of a transistor, those transistors have to be some, they dissipate incredible amount of heat. So if you're talking about a 30-watt amplifier, a fair amount of that is dissipated. That 30 watts is dissipated as heat. And that's just the transistors themselves heating up. Like too hot to touch. Okay, so anyway, these are the switching amplifiers. So class D, E, F, G. I know it goes up to T. I don't know if it's if every letter up through T, but those different letter designations are more specific differences. I just really want to talk about switching amplifiers. So basically, this is a very simple block diagram of what happens. This nice one period sine wave, that's our input signal. And the first thing that happens is that gets converted into a digital signal. That's what this guy does. That C is for comparator. So basically what's going on is the digitizing process is using a comparator. We talked about it before. It's either when the input signal is above the reference, it goes completely high. If the input signal is below the reference, the comparator goes completely low. So the comparator has a digital output, either high or low. What we compare to our input signal that we want to amplify is a much higher frequency triangular wave. So that's this guy. It's a triangular wave that I'm going to compare with my input signal. Once I do that, I've got the digital signal. That goes to a power stage switching transistors. So this is where we amplify the signal. And it's easier to amplify this digital signal because our transistors are either on or off. They're either, you don't have to worry about being in the linear region. It's this gas pedal all the way down or none at all. In that sense, it's easier to amplify that digital signal. But the distortion, I have to worry much less about distortion. So the power stage switching transistors, they're just transistors that can handle higher amount of current. Higher amount of current voltage. So I get this bigger signal coming out, but it is still digital. But so we've only amplified the amplitude, magnitude. The frequency is still going to be the same. So all the spacing between our square waves, our square pulses, that remains constant. It just got taller. And what I mean, so what's important by that spacing not changing is that spacing between these square pulses contains the information from our original signal. So we encoded our analog signal in the different gaps between the square pulses. When I amplify that, I don't change the gaps between those pulses. So I haven't changed any of the frequency, only the amplitude. This next part is pretty cool on how you get your analog signal back out. This LPF, that's just a low pass filter. So you put that amplified train of square pulses into the low pass filter. It filters out all of this high frequency stuff. And what that leaves you is the original analog signal. I think that's a really cool trick. Like you mix a low frequency with a higher frequency, amplify that weird digitized signal, And then you just filter out all of the high frequency stuff. What's left is your amplified analog input. A picture of that. Okay, there's kind of a lot going on in this picture, but the top two, the top half shows the triangular wave oscillator signal, that's like my reference, superimposed on my slower frequency input signal. And I'm comparing those two. So this first part here, my input signal is below the threshold level, so it's off. Comparator says it's below. But as soon as the triangular wave crosses with the input signal here, from this point over to here, my input signal is bigger than my triangular wave signal, so my comparator signal on the bottom goes high. And that just keeps going through the entire process. It works because the triangular wave has a much higher frequency than the input signal. It's kind of sampling your input signal. All right, questions or comments on any of that stuff? This is our segue into, so here's one way that we were able to kind of convert an analog signal into a digital signal. Pulse width modulation is also how FM radio, frequency modulation, that's what this is. Pulse width modulation, modulate the pulse width, you modulate. So yeah, this is like a frequency modulation. Okay, so I'm going to write on the board for this last bit. Okay, I want to convert an analog signal to a digital signal. And before I even want to think about how that works, we got to think about what this actually means. And I'm not trying to be like dumb or joke around, but really, what does it mean to have a digital version of an analog signal? And the best, this is, I think, the best example of that there is. Here's my potentiometer. That is essentially a continuously variable voltage divider, where this would be R1 and this would be R2. So my V out there's V in there. My V out can be any fraction of V continuously variable. That's an analog system. What would a digitized version of potentiometer look like? I would essentially discretize it by making taking this continuously variable voltage divider and making several fixed voltage dividers. So I can either take my output here, here, or here. So I get different this would be like a 2-bit potentiometer where there's 4 possible outputs. So that's the digital version of this. So for me, I don't know. Well, I think a lot of times when I hear digital, I start to think binary. Sometimes, but not all the time. Is that the case? For me, digital, a lot of times it's more like discretized, where instead of having so this potentiometer, its output voltage would be a straight line. What's the output voltage of the thing on the right? Staircase. That's analog, that's digital. Digital and binary are definitely going to be related. But in a sense, this is more digital, is more going to be more discretized. So we're going to build an analog to digital converter. We're not going to build a good one. It's going to be a 1-bit analog to digital converter. 1 bit means there are 2 possible output states, 0, 1, high or low. Okay, so the way that we're going to make this All right. This triangle here, that is my op amp. It's being used as a comparator in this case. Comparing my input signal to the this reference voltage that's coming in to the non-inverting. So for the comparator, the reference input is to the non-inverting op amp. Now, this resistor R1, R2. If I make those guys equal to each other, that's going to be a 50-50 voltage spike. That makes, let's call these both R. So what's the reference voltage if there's sort of the same? This V reference is going to be half of the V reference is going to be half. So what we're doing is comparing my input signal to the halfway point. If it's higher than the halfway point, go positive. If it's lower than the halfway point, go to a negative. This is basically going to convert sine wave into very we would convert a sine wave into a square wave. A 1-bit analog to digital. The 1-bit is giving me my two possible states, either high or low, and I choose my reference to be that midpoint. Either round half of them up or half of them down. So that does convert an analog signal to a digital one. Not very good resolution. How could we make that better? Here, I'm just choosing one point, like higher or lower. How would I do a 2-bit? How many possible values is that going to have? 2 bits. Yeah, 0, 0, 0, 1, 1, 0, or 1, 1. So you have 4 possible states. Up here, the 1-bit had 0 or 1, but we have 2 states. So what is our 2-bit analog to digital converter going to need? If there's 2 states, like this one, how many comparisons do you have to do? So you have to do 1. Is it higher or lower? That's what I'm going to do. 4 states it's kind of like you get 4 different comparisons. That we're comparing 4 different things. How many checks do you have to do to make sure you've got 4 different states? Better check 3 times, not just once. So the 2-bit analog to digital converter we're going to have 4 resistors. 4 resistors makes 3 voltage dividers. 1, 2, 3. Each one of these goes to a comparator, like that. Where all the negatives are on the op amps, the inverting inputs. That's where my input signal goes. I get 1, 2, 3. Three digital outputs. I need 4 states, so there's also a D0. It's just ground. So if we basically how this is going to work, this is kind of like a bar graph meter, LED bar graph meter. If I'm at 1/4 of the voltage, this one would activate. Half this one, 3/4 this one. So each one of these is going to indicate a higher voltage level. D3, D2, D1, and D0 are not the binary output. We'll talk about that next time, because what we need here is something called a 2-bit, not as in bad, but as in just 2 bits. 2 bits priority it's going to look at which one of these 4 inputs has highest priority and output one of these levels for corresponding to that. But we'll talk more about this on Friday, and then the first process, digital to analog. All right. Questions about any of this stuff? General questions? All right, I'll see you guys in lab tomorrow, and we'll pick up on analog to digital stuff on Friday.